Welcome everybody to Space at VT seminar here. This is our last one of the semester. Certainly feel free, don't be shy. Got cookies or whatnot. But today we are joined by a recent. I guess you're going to be graduating technically in a week or so, even though you've already kind of moved on and are taking a gracious break in your work schedule to talk with us today. So today we have Lujain Almarhabi, and going to present just one of hopefully many topics that you covered last week during your dissertation defense.
Yeah. Well, thank you again for inviting me. Yes, I am, I guess technically I was gonna say a recent graduate, but I just technically defended last week, so not yet. And today I'll be presenting some of the results from my thesis. And this is the topic of my thesis was three-dimensional fluid simulations of mid-latitude ionospheric processes with hybrid Chebyshev-Fourier pseudospectral methods. Basically, it's a three-dimensional model for mid-latitude ionospheric processes. Okay, so what I'm going to cover is just a simple introduction, and we'll talk about, what are the governing equations and what are the basic assumptions of the 3D ionospheric model. And I'll cover two results from the 3D model that were interesting. The first one is, 3D modeling of GDI and KHI in ionospheric plasma clouds, and the second one is looking at 3D GDI and KHI in SAPS with parallel dynamics. And so I just want to start with a brief introduction about the ionosphere. And, we know the ionosphere is the electrically charged portion of Earth's atmosphere. It's a partially ionized gas where, due to gravity, is stratified into regions. These regions are, they're known to be D, E, and F. And these regions can be also categorized based on the electron number density. And on the left, I have a panel showing the neutral particle density with respect to altitude. And I'll talk a little bit more why we care about this. But basically, we know that neutral particle density is also changing with altitude, which means that the ion collision frequencies will be changing with altitude. And this implies that each one of these regions in the ionosphere are going to have very distinct, dynamics, basically based on altitudes. And for my work, I only focused on basically the F region and the altitudinal variations in the F region. And so a little bit of motivation, basically, what is ionospheric turbulence? So it's basically disturbance in the plasma density on the ionosphere, then can have negative impact on, GPS radio signals. So on the right, we have this exaggerated kind of figure showing what a GPS radio or a radio signal passing through a turbulent region can, have an impact on. It can cause shifts in the amplitude and phase of the wave, and that negatively impacts some position estimates, the accuracy of position estimates of GPS signals. And for us, or for me, a person or a plasma physicist, we care about the sources behind these or the generation mechanism behind ionospheric turbulence. And so, it's hypothesized that, plasma instabilities, the presence of plasma instabilities are the reason behind ionospheric turbulence. And there are various types of plasma instabilities that can cause this. But for my thesis, I looked at only the gradient drift instability and Kelvin-Helmholtz instability as two primary instabilities in the F region that causing the major structuring. They are major sources of structuring in the F region ionosphere. And so we look at the first primary instability we care about is the gradient drift instability. It's an interchange instability. And on the right here, I have a diagram showing the generation and the growth mechanism of the GDI. So we have in the F region, there's a requirement for GDI to happen, and that is we require a component of each, the electric field, density gradient, and magnetic field to be orthogonal to each other. And if we have a difference in the ion neutral collision frequencies, that leads to an induced a Peterson current that causes charge separations, and that gives us a perturbed electric field that is represented with delta E in the diagram on the right. And delta E can interact with the background magnetic field, and that leads to an E cross B drift, or a perturbed E cross B drift, here shown as delta V. And basically this geometry becomes it's a destabilizing geometry, so the GDI will grow, and without any immediate damping mechanism, we expect the the GDI to grow without any damping. And so I want to just like briefly talk about the growth rates from a theoretical perspective, and we have a very simplified growth rate expression from linear theory. That is equation 1 for this is for GDI in the F region, and it depends on the magnetic field, density, gradient scaling, and for an arbitrary geometry, we can represent the growth rate as equation 2, where K is going to be the wave number vector, B is the magnetic field, G is density gradient, and E is the electric field, and they're all vectors. And here R is a dimensionless parameter. It's a dimensionless collision parameter that is represented with equation 3, and we'll talk about this one as well later. And equation 2 can be also simplified further. And in particular in the F region, we can say that, we take the assumption that, collisional effects are, can be negligible in the F region, and we can look at the GDI only at the short wavelength limit. And then the last term will drop, and we'll have a simpler GDI growth rate expression. So the second primary instability here we look at is the Kelvin-Helmholtz instability, and this one is it's a fluid instability or shear instability. You have different velocities across an interface that a small perturbation can lead to like a vortices-like structures, or vortices-like formations. And we know like Kelvin-Helmholtz are ubiquitous in nature, so you see them from your morning cup of coffee when you add a little creamer to it, to waves and in the ocean, or in this case we have KHI in clouds. This picture was taken from Wyoming in 2022. So, and finally, I just want to talk briefly about subauroral polarization streams, or SAPS. And these are regions in the mid-latitude ionosphere with where poleward electric fields drives a large westward plasma flow, and usually they're associated with density troughs. And we'll talk a little more about SAPS, but the reason we care about it is that observations, ground-based observations have shown that there are density irregularities presence in SAPS that are thought to be caused by plasma instabilities such as GDI and KHI. So as I said, we'll talk more about SAPS as well. So basically the work for my thesis, what was the proposed work is that, there was a previous 2D model, and I took that model and extended it to a 3D model. And the goal was to, implement different boundary conditions with respect to altitude. And so we can include physics that is associated with motion, not only perpendicular to the magnetic field, but also parallel to the magnetic field. And the model, the 3D model, addressed issues that were in previous 3D models, such as unrealistic aspects of 3D simulations of plasma clouds, neglecting ion inertial terms. We'll also talk about that as well. And the key novelty in this 3D model compared to the previous 2D model is the inclusion of resistive electron motion in parallel dynamics. And we'll see how that introduces new physics in the 3D model. And finally, the goal was and is still that we can use this 3D model to study, other types of ionospheric turbulence generating phenomena, such as SAPS or polar caps, and not just limited to one phenomenon. So these are my governing equations, the three-dimensional governing equations that we're using. And equation 9 is basically like a mass conservation, so it's continuity. And equation 10 is going to be, it's a very important equation for us, and it's charge conservation, or referred to current closure, or sometimes I'll say potential equation. And in equation 10, we're showing like underlying important terms and what, physics associated with it. So we have on the left-hand side, we have KHI development. These are terms that are going to be associated with any inertial effects. And GDI development is basically, terms that are going to be associated with the development of gradient drift instability. And asymmetry here is associated with pressure terms, and we're going to talk about it as well later. And finally, we have, N is density, just phi is our electric potential, and D is a numerical diffusion term. U is the neutral wind, and we have the collision frequencies as well. Let me see. Sorry about that. Okay. So equation 10 can be also rewritten into the its parallel and perpendicular terms, and it's important to just like point out some of the physics and the parallel dynamics in the potential equation. So the terms are grouped into equation 1 and 2, where equation 1 is going to represent terms that arise from ion cross field current. And then terms with the grouped under 2 are going to arise from divergence of parallel electric current. And the ion cross field current, or these are like motion associated with the perpendicular that are perpendicular to the magnetic field, can also be split into 3 other terms that are shown on the upper right corner of the slide. The first term is associated or arise from Peterson current. The second is diffusion associated with ion neutral collisions. And then the third term is associated with basically drag between background neutral wind and ions. Yes, ions. And so the basic assumptions is that, first of all, the model is using these numerical methods. We are using pseudospectral methods for spatial discretization, and we're using Runge-Kutta for temporal integration. And the current closure, the equation that we just showed, is solved iteratively because it's highly nonlinear. And the model assumptions are that we are assuming the magnetic field to be completely aligned with the z-axis or the altitude direction. And we're assuming quasi-neutrality, so the electron and ion densities are equal. And the model is associated with large-scale motion, so E cross B drifts, basically it resolves time scales associated with E cross B drifts or diamagnetic drifts, and not like plasma frequencies or gyro frequencies. And we are using electrostatic approximation, which is a good approximation for the F region. And finally, the model is a perturbed model, so it's taken the total variables and splitting it into perturbed and background components. So the first result we looked at is we used the three-dimensional model to look at the evolution of ionospheric plasma clouds. And I just want to briefly talk about what are plasma clouds, basically. And so these are experiments that involve releases of metallic vapors or molecular vapors into the atmosphere or ionosphere that can be ionized through photoionization, and they can also show structuring due to the presence of GDI or KHI. And these are usually historically have been used for diagnostic methods, so they are used to study the atmospheric parameters or plasma flows, and so they are of great importance for the I guess the space physics community. And the reason we chose plasma clouds here is well, it's an aesthetically pleasing problem. We can combine two types of plasma instabilities into one, and we see the effect of both of them in a plasma cloud. And the second reason is that the 3D model, there are previous 3D models that have looked into plasma clouds with great detail, so we can use these results to compare to previous 3D models and validate our current 3D model. So the density here was modeled using a Gaussian type function that looks like that. It's a 3D with respect to X, Y, and Z. And then on the right, we have a diagram showing the plasma cloud. It's like a spherical cloud with high plasma density in the middle and then low plasma density in the background. We have R representing our radius, and B is along the Z axis. The neutral wind is going to be along the positive X axis, and so we expect the leading edge of the cloud or along the neutral wind to be unstable to the GDI. And we looked at two regimes here, a highly collisional regime, or this is a regime represents the lower F region in the ionosphere, so it's about 200 kilometer, and then an inertial regime, which is higher F region, where it's about like 450 kilometer altitude. So for the first result is we are comparing our 3D results to 2D results. So we're using the previous two-dimensional model, and then we're using the current 3D model. On the left, we have results from 2D, and then on the right, these are results for 3D. And we're looking at a highly collisional regime, so about 200 kilometer. We see on the right, we have color density plots of the plasma cloud. And we see that we expect the cloud to be drifting along the neutral wind direction, so along the positive x-axis. And as the cloud is moving, we notice that the leading edge becomes unstable to the GDI, and we see a GDI-induced bifurcation. So the cloud starts like looking like a Pac-Man sort of, and then it becomes even unstable to a secondary GDI, where like we see this like finger-like structures emerging from the middle of the cloud between panel D and F. And in the 3D result, we have a very similar behavior between panel A and C. So the cloud is drifting along the right axis, the positive axis, the right direction. And we see this GDI-induced bifurcation. And at panel D, things start looking different. So the GDI starts, we see these finger-like structures which are associated with the gradient difference stability, and they start like almost like rotating about the cloud. So we look at this in closer look, and we can look at so both these panels represent 3D results. On the left, we are taking a slice in the y-axis and we're plotting XZ plane. And then on the right, we are taking a slice in z-axis and we're looking at the XY plane. And these are all at the midplane of z and midplane of y. And so we see in the XZ plane on the left side that there are these very fine finger-like structures between shown in panel D and F. And this represents basically a gradient drift instability. This is a very interesting result because we expect the GDI, well, basically the GDI is known to be a flute-like instability, which means that it's an instability that generates fluctuations, density fluctuations perpendicular to the magnetic field. And here what we see is that there are fluctuations that are parallel to the magnetic field, which means that the addition of the three-dimensional effects is like kind of altering these flute-like characteristics of the GDI. This comes from the current closure equation or the potential equation, where there was a term indicated with asymmetry, and I said we will look into this later. These terms are represented by the parallel electron pressure terms. So basically adding these terms, it introduces an ambipolar potential in the potential equation that produces a twist or it forces the cloud to rotate about its center field align axis or the z-axis. And basically, because the propagation rate is not uniform across the cloud, so as we move upward away from the midplane of z, we expect the propagation rate to increase. This causes the cloud to like shear. It has this looking like shear kind of and you can see it in panel C to F, and this is caused by the introduction of the ambipolar potential. So these results are also consistent with previous three-dimensional model. This particular configuration is called Barbour pole configuration. where the introduction of the electron parallel pressure terms introduces an ambipolar potential that causes the cloud to shear about its center field aligned axes. And we are able to see this too in the 3D model. So for the inertial regime, we have on the left represent 2D. These are the 2D results. On the right, we have the 3D results. And basically, we see very similar results in the inertial regime. The plasma cloud is drifting along the right direction, and then there's a finger-like structure emerging from the center of the cloud, which is the GDI, and then it becomes unstable to a secondary KHI. This is represented by these mushroom heads-like structures. And in later stages, we see that the structuring process is dominated fully by the presence of KHI, which is expected in an inertial regime. The only difference is between 2D and 3D is we visually see a slower growth rate. So the cloud is structuring basically in a slower aspect. This is also consistent with the physical description of previous 3D models. So this is not a quantitative kind of result. This is more like a qualitative description that most previous 3D models that investigate plasma clouds describe as well. So we have results that are consistent with the previous models, 3D models of plasma clouds, and we can validate our model, and we use these results to like build on the new 3D model with the inclusion of full parallel dynamics and altitudinal variations as well. So for the newest results, we use the 3D model with altitudinal variations to look at GDI and KHI in SAPS. And this is the geometry in 3D. We have on the left a geometry of SAPS in 3D where X is going to be my north here, Y is east, and therefore that gives me a westward velocity, SAPS velocity in negative Y, represented by Vy, and I have neutral wind along the negative x-axis, or we refer to it as meridional direction. And we have, because of the density and the velocity, the SAPS density and velocity profiles have latitudinal profiles. This introduces gradients in the density and the velocity, represented by density gradient N and gradient Vy, and the positive and negative x-axes. And Z here is down. So the boundary conditions here are periodic in X and Y, and they're going to be non-periodic in Z or zero Dirichlet boundary conditions. And what that means is that we're assuming that no perturbations occur past the boundaries. And this is an okay assumption right now because we are enforcing our boundary conditions on perturbed variables since it's a perturbed model and not on the total variables. And so if we take a slice in Z, right, and we try to represent that in an XY plane, we see the diagram on the right. This is a slice in altitude in Z, and we plot an XY domain where we have a density gradient along the positive x-axis. We have the neutral wind along negative x-axis. The neutral wind interacting with the background dense magnetic field that gives us an electric field along the positive y-axis. And so to initialize my model for the three-dimensional SAPS is I split or categorize our ionospheric parameters into two categories. The first one is altitude dependent, and these are going to vary with altitude, and the other ones are going to be constant with altitude, and these are going to be based on nominal off-region ionospheric values at 300 kilometer. We're assuming dominant species is going to be oxygen. We're taking, temperature, electron and ion temperatures at 300 kilometer. And for the neutral wind, we're, for these runs, assuming that it's temporally and spatially constant and is being chosen based on like a upper end kind of observation, like values from observations that fall under, I guess, strong geomagnetic conditions. And it's chosen in particular in our model, so it can be like inducing of a GDI. And so for the other parameters, the altitude variational parameters, we start with the neutral profile. We use a barometric formula, which is basically represents the distribution of neutral particle density with respect to in a gravitational field. So we use that, and we where n base here is going to be my neutral density at a reference altitude. Here is chosen 200 kilometer, and the scale height is going to be for atomic oxygen in the F region, and it's both are calculated with this shown at with the table. And then if we plot this result, we have a density profile, a neutral density profile with respect to altitude, where it's dropping with respect to altitude as we expect. And then for the plasma density, we're using a Chapman layer function, and it basically N max is going to be the plasma density, the peak plasma density at F peak, which is 300 kilometer. And we calculate the scale height similarly, and we can plot this profile on the right, showing this is what an expected Chapman layer-like function to look like. So for the SAPS profile on the left, here we have Superdone SAPS and GPS total electron content trough density profiles. These were based on data that was collected by Dr. Kanduri from Superdone Group. And on the right, we have the data approximation of these SAPS profiles as initial conditions in 3D. And they're taking at 300 kilometer altitude. So W represents the largest width of minimal velocity shear, or basically it's like the SAPS channel. And since, the background density now is a function of altitude as well, basically these density trough profiles will vary with altitude, and I can take slices at different altitudes to show each one of these density trough profiles at different altitudes. And you can see the plasma density is changing, like the magnitude of plasma density is changing. And for simplicity, we're assuming that the velocity profile right now is fixed with altitude. And so we go back to equation 1, where we say that, from linear theory, we have a very simplified growth rate equation for the F region, where, it depends on the density gradient, scale length, and the magnetic field and neutral wind. And the linear theory predicts that, the growth rate will drop with respect to altitude as you're going higher in altitude, which indicates or that implies that inertial effects are becoming more dominant, and, an instability like KHI will be more dominant at higher altitudes. So here we're just like quantifying some of our results. We look at the simplified growth rate at different altitudes. And this is a very quick animation. Basically, I just want to say that the full range of altitude for this simulation is 200 to 700 kilometer, but I'm looking only at a 200 to 450 kilometer with the dynamics happening there. And we can talk a little bit about what happens above that altitude. But basically on the left, I have the parameters used for this run. This is a week-long run, but here I'm like, making it fast so we can just look at the variations with respect to altitude, what happens, and we can take a closer look. So on the left, I have the initial conditions. These are three-dimensional isosurfaces where each isosurface or each density trough represents a specific plasma density value. And then on the right, I'm looking at the later time stage of that simulation, where I can see all the instabilities at different altitudes. So at lower altitudes, we see a GDI, and then at higher altitudes, we see these vortices-like structures representing a Kelvin Helmholtz instability. And then in the middle, there's a prediction of a transitional region where both GDI and KHI can coexist together. And you probably can't see the GDI from this angle, so I switched the angle basically, so you see these kind of finger-like structures on the right trough, on the right interface of the 3D isosurface, representing the GDI. And this, we already can predict from 2D models that, we expect the GDI to dominate at lower altitudes, or altitudes where we have more collisional parameters, like a collisional regime. And then at higher altitudes, we expect the KHI to dominate at where inertial effects are getting more dominant. And so we take the last time frame and we try to slice different altitudes, and we will plot a two-dimensional color plots to further investigate. So here we are looking at two altitudes. First is the collisional altitude. This is where we expect the collisional parameters to dominate. And on the right, we have higher altitudes of 326 kilometer, where we expect the inertial effects to dominate. And we see that we have a finger-like structures. As we expect, we see the GDI developing there. And then on the right, we have the Kelvin-Helmholtz instability with the vortices-like structure dominating at higher altitudes. And we can look at the transitional region where it starts with about 235 kilometer, and then I am looking at 264 kilometer. And, on the left, we can see, the shear, like Kelvin-Helmholtz, developing. And then the GDI, the finger-like structures, are also very present. And as you move forward, as you move higher in altitude and to the right in this plot, the basically collisional effects are becoming less dominant and the inertial effects are getting more dominant. So we expect that the GDI to become to diminish and the Kelvin-Helmholtz to become more and more like dominant, as we can see here. The vortices are developing more. And now we can basically characterize the effect of collisions by looking at this parameter that we briefly mentioned early on, which is the dimensionless collisional parameter R. And we calculate this R at two altitudes, the GDI, where the GDI dominates, and where the KHI dominates. And we represent this on the right. You can see the yellow represents the GDI R value, and the orange or brown represents the KHI value. And this plot shows what this plot shows is that basically for anything below the yellow dashed line, we expect the GDI to dominate, and anything above the KHI dash line, we expect the KHI to dominate. We also here have this horizontal dash gray line representing the altitude where superdawn operates, and this is of interest for us as well for reasons I'll mention later. And so I take this plot and try to compare it to previous similar calculations in 2D. This is on the right, I have a results from two-dimensional model. This is from literature, and I highlight only the top panel, which is similar to our, simulations parameters, basically. And we notice few things. It's like the altitudes where GDI and KHI dominates are very different. And I want to point out that the plot on the right, this is from a 2D model that is using ionospheric models like MSIS, IRI, IGRF to vary all the ionospheric parameters with respect to altitude. So not only the plasma density, neutral density, but also magnetic field temperatures, and it's also taking in consideration all the correct species with respect to ionosphere. In the ionosphere with respect to altitude. So the plot on the right represents more of a prediction of what we expect the GDI and KHI to behave with respect to altitude using more like empirical data and not simulation data or parameters. And on the left, this is my plot using the 3D model where I initialized where I'm varying only two parameters with respect to altitude, which are the plasma density and neutral density, and everything else is held fixed. And we basically see the same behavior. Yes, the altitudes are off where the GDI and KHI are dominating, but the value of R for GDI and KHI falls within the same like basic order of magnitude to the previous 2D results. And the region in between the transitional region that was predicted by the 2D model is also very similar, and it falls within the same range of values. So what we're saying here is that the 3D model is basically solidifying the prediction that previous 2D models were making based on empirical data. And finally, I just looked at some turbulence spectra. This is of interest for us as well. And, I have here the power spectra of the perturbed density normalized to the total density, and the perturbed potential, electric potential, also normalized to the total potential. And for two different altitudes, this one is the higher altitudes where we expect the KHI to dominate, and it gives us power laws of -1, -3 for the perturbed density and electric potential respectively, which is consistent with nonlinear theory and also observations. And the second one is for the lower altitude where the GDI dominates at 219 kilometers. And this gives us a power law of -6 and -8. It's a steeper slope, and these results are also consistent with previous 2D results of GDI in SAPS. So basically, to summarize, we looked at 3D model with no altitude variations, and we looked at the evolution of ionospheric plasma clouds. These results were published in Atmosphere, a journal in 2023, and then the new 3D model with the full altitude variations, the altitudinal variations, using different types of boundary conditions, and this model is also parallelized, was able to demonstrate, merit to previous predictions by 2D models in literature, and it will hopefully help, people like Superdon people to look at interesting problems for future observations to investigate. And for the future work, we divide it to short term and long term. Basically, I focus on the short term, which right now we're looking at 200 to 700 kilometer. We would like to extend that range to 800 kilometer because that will include other operational range. It will include the operational range of satellites. For example, right now we can compare only to Superdon that looks at SAPS at 300 kilometer, but there are, for example, the DMSP satellite that looks at SAPS at 800 kilometers. So that would be of great interest for us to look at the entire range. And we can also recalculate some of the ionospheric profiles to have more realistic or better inputs, and vary the introduce altitudinal varying profiles for temperature and magnetic field. And obviously, higher resolution simulations will help us with much better, or improve our turbulence spectral analysis. And this is for me, trying to add a better calculation of GDI growth rates, looking at numerical growth rates and not just simpler theoretical growth rate calculations. And for long term, we'd like to implement different boundary conditions, expand the model to be multi-ion species, and investigate the impact of altitudinal dependent neutral wind profiles to study all the impact on the instability growth rates. And these are my publications, only the first two, and then the third one is future, hopefully. And then I'm also a co-author at another publication that is under consideration right now. Yep. So I'll stop here and I'll stop sharing just in case. Oh, my okay.
Yeah, thank you very much. Yeah, any questions?
I apologize. I got a phone call in the middle that I had to take, but you were talking about TIDs for a little bit there, I think. And
you mean like SAPS?
SAP, sorry about that. I guess I came wrong. Can you tell me a little bit about the scale, and is there any way you could think of that we could see those in airglow? I know we're looking for effects in nitric oxide and things like that, but I'm just wondering, for a neutral observer, what are the other ways we could see that?
Yeah, so I am working with, Professor Wanami was on my committee, so he provides a lot of valuable insight when it comes to observations. So I guess your question in particular, are you talking about air glow?
It could be air glow, it could be temperature. Is there an effect on winds? Is there any other way to see it?
The effective winds, I can't really talk about that yet because we're, simplifying our, assumptions by taking something, a neutral wind based on observations, right? But I guess if you can give me a specific example that I can show.
Oh no, that's what I'm asking you. We're working on proposals to do observations, and I'm wondering if it's possible to see those in observations we're making.
I guess yes, maybe you can in particular altitudes. It depends on what if you're using ground-based or satellites, I'm not sure. So if you're using ground-based, about 300 kilometer, we were able to, some of our results we were able to match with observations from Superdon, or there's in particular the DMSP satellite at 800 kilometer as well. But I think for better comparisons, maybe for this in particular, the 3D model, we need much higher resolution, right? to be able to capture these spatial scales that you guys
Yeah.
are looking at. Right now, I am looking at a few hundred meters.
Way too small for us.
You need something better, I think, right?
Yep.
But that is doable. I have parallelized my code. It's just that someone else is running these results.
Yeah, and we can't paralyze our instruments, but
Yes. But
just curious. Thank you.
yeah.
Yeah, it's Mike here, sort of lurking in the background. I had lots of questions for Lujain last week during her PhD defense. Scott, you definitely see gravity waves in air glow. I mean, that's one of the standard ways of mapping or observing and mapping passage of gravity waves.
Well, no question about that, but SAPS specifically.
Oh, SAPS. Oh, okay, yeah, I may have misunderstood.
Yeah.
There, I'm not sure. I don't know if anybody's looked at that. Nothing occurs to me.
Okay. All right. Thank you.
Any other questions?
I also can take questions on email through email if you want.
Yeah, I say, well, maybe not press it too hard. As again, John's just been through a PhD defense and moving and starting a new job, and actually is taking a break from her job. So maybe we'll give her some time back and let her get back to work, basically in a new position there. So
Congratulations.
Thank you so much. Yes.
Congratulations.
Thank you.
I wish I understood more of it.
Double congratulations.
Move in the new job.
Yes, thanks.
Where are you? Where is the job?
I am in Washington State.
Nice. Okay.
Yeah.
Well, good. Thank you very much for joining us, and everybody here too joining us today. This is the last one, Space of ET seminar for the semester, and we'll start back up within the new spring semester within the first week or two. But look for announcements then. But otherwise, yeah, thank you very much, and everybody, good luck with finals, and have a good end of the year break.
Yeah. Thank you again, Kevin.
Thank you all. Thank you for the seminar. It was great.
Right.
Thank you.
Take care.